Hello everyone. Today we will be seeing few more results related to sequences. So the first result that we will prove is if two sequences differ only at finitely many places, then both of them will have same limiting behavior. Okay. Uh, in the earlier lecture we have proved uniqueness of limit. So we have proved that if a sequence converges, then its limit must be unique. So let me state the result that we are going to prove today. So suppose that xn and yn are two sequences which differ only for finitely many natural numbers, only for finitely many natural numbers. Further, suppose xn converges to x. Suppose xn converges to x. Then we have to prove that yn will also converge to same limit x. Okay. So let me try to first explain what is happening here. So I have two sequences xn and yn which differ only at finitely many places. What do I mean by that? That except for those places, for all other natural numbers, xn is equal to yn. Okay. So let me try to write. So this means xn is equal to yn if n doesn't belong to some set m, okay, where m is a finite subset of set of natural numbers. Okay. So what do I mean by that? M is a collection of numbers. M is a collection of those natural numbers for which xn is not equal to yn. So m is finite, and for rest of the n's, xn is equal to yn. Okay. Then our claim is that if xn converges to x, then yn also converges to x. And in fact, we can also say that if xn doesn't converge, then yn will also be a non-convergent sequence. How do I prove this first part? Okay, xn converges to x. See, what I know is that xn and yn differ only at finitely many places, and those indices are collected in n. Now, can I say that every finite subset of set of natural numbers is bounded above? Just think, if you consider any finite subset, it will have a largest element, and that largest element will be an upper bound. Okay. So, since m is a finite subset of n, there exists n1 in n such that m is less than or equal to n1 for every m in m. That is, this set m is bounded. Think of any finite subset. Because it is finite, you will have one element which is largest, which is last element. Okay. So m is less than or equal to n1 for every m in m. Now, what I know is xn converges to x. So, given epsilon greater than 0, there exists n2 in n such that mod xn minus x is less than epsilon for every n greater than or equal to n2. Okay. Now, let me define n0 as maximum of n1 comma n2. Okay. Let me define n0 as maximum of n1 comma n2. Now, since n0 is larger than n1, n0 is larger than n1 would imply that for every n greater than n naught, n cannot belong to M because all the elements in M are smaller than n1 and n1 is further smaller than n naught. So no number larger than n naught can be in M. This implies that for every n greater than or equal to n naught, xn will be equal to yn, because if they are unequal then that n will belong to M, which is a contradiction because M has n1 as an upper bound. So for every n after n naught, xn is equal to yn. Okay, and for every n after n naught, we know mod xn minus x is also less than epsilon because n2 is also smaller than n naught. So this implies mod xn minus x is same as mod yn minus x because xn and yn are same, and this is less than epsilon for every n greater than or equal to n naught. Thus, given epsilon greater than 0, we have been able to find n naught such that mod yn minus x is less than epsilon for every n greater than or equal to n naught, and therefore yn converges to x. Okay. How do you prove the other thing? Means if suppose xn and yn differ at finitely many places, and further suppose that xn does not converge, then how would I prove that yn doesn't converge? We can prove that by contradiction. Okay, because if suppose yn converges, then by the result that we proved just now, xn would also converge to the same point, which would be a contradiction because it has been given to us that xn doesn't converge. Hence, xn and yn both will become non-convergent sequences. Is it okay? So try to write down that part of the proof on your own as homework. Okay, so what is homework? Homework is if xn, yn differ at finitely many n's, if xn and yn differ at finitely many n's, and if xn is a non-convergent sequence, then yn is also a non-convergent sequence. I've already discussed the proof orally. Your job is just to write it down. Okay, yn is also a non-convergent sequence. Okay. Now let me study few more results related to sequences. We will state the results and we will try to prove them one by one. So what are the results? Let xn be a sequence of real numbers. Okay, let xn be a sequence of real numbers. If xn converges to x, then mod xn converges to mod x, but the converse is not true. That is, if mod xn converges to mod x, that does not necessarily mean that xn converges to x. Next result is xn converges to 0 if and only if mod xn converges to 0. So in the first case, if the limiting value is 0, then the converse is also true. And the third result is xn converges to x if and only if mod of xn minus x goes to 0. Okay. Let me try to prove these three results one by one. First, we have to prove that xn converges to x implies mod xn converges to mod x. For that, we are going to use one inequality and it's your job to prove that inequality as a homework. Okay. So what is the homework? Let me state that because we are going to use that. So homework is to prove that mod of mod xn minus mod x, this is what we need. Let me write in general terms. Mod of mod a minus mod b is less than or equal to mod of a minus b. Okay, you have to prove this. Mod of mod a minus mod b is less than or equal to mod a minus b. It is quite easy to prove. You just have to use triangle inequality and then the definition of modulus, nothing else. Okay, so this is homework. By using this, now we will prove part 1. So we will write, we have to prove mod xn converges to mod x. So we have to prove that given epsilon greater than 0, there exists n such that mod of mod xn minus mod x becomes less than epsilon. And what is given to us is xn converges to x. Okay, so let me use that. Xn converges to x implies given epsilon greater than 0, there exists n naught in n such that mod xn minus x is less than epsilon for every n greater than or equal to n naught. Now using this result from the homework, I can write mod of mod xn minus mod x is less than or equal to mod of xn minus x, which I already know is less than epsilon for every n greater than or equal to n naught. So this implies mod of mod xn minus mod x is less than epsilon for every n greater than or equal to n naught. And this is nothing but definition of convergence of mod xn to mod x. So this implies mod xn converges to mod x. Okay. So if I use this result, then the proof becomes very straightforward. And the converse is not true. We all know if I define xn equal to minus 1 raised to n, then mod xn converges to 1, but xn does not converge to any number. Okay. So the converse is not true. Next result is xn going to 0 if and only if mod xn is going to 0. This is also pretty straightforward because the what I have to prove is mod xn, suppose mod xn converges to 0 is given, because one way anyway we have proved. We have to prove only the other way. So suppose mod xn converges to 0. This implies given epsilon greater than 0, there exists n naught in n such that mod xn minus 0 is less than epsilon for every n greater than or equal to n naught, and mod of mod xn is nothing but mod xn. So this implies mod xn is less than epsilon for every n greater than or equal to n naught, and this implies what? Mod of xn minus 0 is less than epsilon for every n greater than or equal to n naught, which is nothing but definition of xn converging to 0. Okay. The third result is basically a consequence of second result. So I will leave that as homework. Okay. Now let me state next result, which is also quite important. So suppose xn is a sequence of real numbers converging to a positive number. Okay, xn is a sequence of real numbers converging to a positive real number x, converging to a positive real number x. Then there exists a natural number n1 such that such that xn is greater than x by 2 for every n greater than or equal to n1. Okay, xn is greater than x by 2 for every n greater than or equal to n1. Let us draw the picture and then life will be easy. So I have 0 here. We know x is positive, so x is somewhere here. X by 2 is somewhere over here. So we want to claim that after a finite, if I leave out few finitely many terms, then all the terms are here to the right of x by 2. Can you see that this is obvious from the definition of convergence? From the definition of convergence, we know that after a finitely many terms, all the terms can be made to come inside a neighborhood. So if I construct my neighborhood in such a way that my neighborhood is like this, my neighborhood is completely to the right of x by 2, then after a finitely many terms, all the terms will be inside this neighborhood. That is, all the terms will be larger than x by 2. Correct? That is exactly the idea. Okay. So we know that xn converges to x. So choose epsilon in such a way that x minus epsilon should be to the right of x by 2, which means epsilon should be less than difference between x and x minus 2. That is, epsilon should be less than x by 2. Okay, so choose epsilon less than x by 2. Given this epsilon, there exists n naught in n such that mod of xn minus x is less than epsilon for every n greater than or equal to that n naught. Okay, thus this would imply that x minus epsilon is less than xn is less than x plus epsilon for every n greater than or equal to n naught. But what I know is epsilon is smaller than x by 2. So x minus epsilon is larger than x minus x by 2, which is equal to x by 2. Therefore, x by 2 is less than x minus epsilon is less than xn is less than x plus epsilon for every n greater than or equal to n naught. Therefore, xn is greater than x by 2 for every n greater than or equal to this n naught, and that same n naught I can take as n1. Okay. In fact, this actually tells me that if xn is a sequence converging to a positive number, then at most finitely many terms from this sequence can be negative. Okay. At most finitely many terms from this sequence can be negative because they all are greater than x by 2, means they all are positive. You cannot have infinitely many negative terms. Is it okay? Similar result will hold for negative numbers. That is, if xn converges to a negative number x, then at most finitely many terms will be positive, rest of the terms will be negative. We can actually combine this into a more general result. Let me write that result. So let xn be a real sequence with xn converging to x. Further, suppose that x is non-zero. Suppose that x is not equal to 0. Then there exists a naught in n such that mod xn is larger than or equal to mod x by 2 for every n greater than or equal to that n naught. Okay, mod xn is larger than or equal to mod x by 2 for every n greater than or equal to n naught. Okay, so we have done it for positive x. So for general x, there is another way in which we can prove. So instead of taking epsilon as less than x by 2, now I'll have to define epsilon as less than mod x by 2. Okay, take epsilon less than mod x by 2. So this implies mod x, I can write mod x as mod of x minus xn plus xn. This is less than or equal to mod of x minus xn plus mod xn. And given epsilon greater than 0, because xn is converging to x, I can make this smaller than epsilon and this stays as mod xn. Okay, so this would imply mod xn is larger than mod x minus epsilon. Okay, but I know that epsilon is smaller than x by 2. So this is larger than mod x minus mod x by 2, which is equal to mod x by 2. Hence, mod xn is larger than mod x by 2 for every n greater than or equal to n naught. So somewhere here I have to write, take that given this epsilon, there exists n naught such that mod of xn minus x is less than epsilon. Okay. Now we will prove one more result, important result related to convergent sequences. So we will prove that every convergent sequence is bounded. Okay, every convergent sequence is bounded. So first I have to start with a convergent sequence. Consider xn a real sequence converging to x. Okay, what I know is after a stage, like after leaving out few finitely many terms, all the terms of that sequence, all the terms of a convergent sequence are inside a neighborhood. Okay, so let me draw picture. X is here. What I know is after a certain stage, all the terms of xn are here in x minus epsilon to x plus epsilon. So x plus epsilon is obviously an upper bound for those terms. So I have to worry about only those finitely many left out terms. Okay, so let me make it more formal. Given epsilon greater than 0, because of convergence, given epsilon greater than 0, there exists n naught in n such that mod xn minus x is less than epsilon for every n greater than or equal to n naught. Okay, so in particular, if you want, you can take epsilon equal to some number, let's say 1 or 0.5. Okay, so if I take, so for example, if epsilon is equal to 1, then this would imply mod xn minus x is less than 1 for every n greater than or equal to n naught. This would imply x minus 1 is less than xn is less than x plus 1. Okay, x minus 1 is less than xn is less than x plus 1. And this is true for every n greater than or equal to n naught. And we already know that there are only finitely many terms outside. So let m naught be maximum of x1, x2 up to xn naught minus 1. These are finitely many numbers, so of course they have a maximum. So let m naught be maximum of this. So this would imply if I define M as maximum of M naught comma x plus 1, if I define M as maximum of M naught comma x plus 1, then xn is less than or equal to M for every n, because x1, x2, xn naught minus 1 are smaller than this M naught, and all the all the terms with higher n, that is xn naught plus 1 and so on, they are smaller than this x plus 1. So when I take maximum of these two, it becomes a common upper bound for all these terms. Okay, so same story I can do with lower bound. Okay, so let small m naught be minimum of x1, x2, xn naught minus 1. So xi is larger than or equal to m naught for every I equal to 1 to up to n naught minus 1. And we already know that x minus 1 is a lower bound for further terms. Correct? X minus 1 is less than xn for all these. So if I define m as now minimum of m naught comma x minus 1, then xn is larger than or equal to this m for every n. Okay, therefore I have an upper bound as well as a lower bound. Okay, if you want a common bound, you will say mod xn is smaller than modulus of m, modulus of small m and modulus of large m. So whichever is maximum, modulus of small m or modulus of large m, that would become a common bound for mod xn. Okay, so we have just now proved that every convergent sequence is bounded. But does it mean that every bounded sequence is convergent? No. Again, we can use the same example, minus 1 raised to n. That sequence we know takes only two types of terms, minus 1 plus 1, minus 1 plus 1. So the sequence is obviously bounded by minus 1 and plus 1. However, it is a sequence which oscillates within that interval, and hence it does not converge. Okay, so let me stop here for today. We'll continue in the next lecture. Thank you.